Imagine you ask a math tutor to solve a hard problem. They write down a sequence of plausible steps and arrive at the correct answer. A human teacher checks each intermediate step. But what if the steps are nonsense yet still lead to the right final answer? That student might learn bad reasoning habits. Modern large language models, or LLMs, are increasingly trained to produce step-by-step explanations, called chain-of-thought reasoning, to make their thinking visible and improve performance. The most popular training method is reinforcement learning, RL, that gives a reward only when the final answer is correct. This lesson examines a recent paper showing that this outcome-only RL training actually makes models more likely to fabricate unsupported claims, a problem known as hallucination. We will walk through the evidence, the theoretical reasons involving gradient variance, exploration pressure, and local traps, and then a modified algorithm called FSPO that checks each reasoning step against external evidence to reduce the trade-off. By the end, you will understand the core design pattern for rewarding factual steps rather than just final correctness. The paper starts by comparing several model families. For each family, they evaluate a base model without large-scale RL, like DeepSeek v3 or QWEN 2.5 Instruct, and the RL fine-tuned or distilled version, like DeepSeek R1 or WQ. On 3 standard hallucination benchmarks, Truthful QA, HalluEval, and HalluQA, the RL-tuned models show consistently higher hallucination rates. For example, DeepSeek R1 hallucinates much more than its base DeepSeek v3. To understand why the authors manually inspect 200 samples where the base model answered correctly, but the RL version did not. The dominant error category is intermediate reasoning error. The reasoning steps contain incorrect or fabricated claims even if the final answer sometimes is correct. This confirms that outcome-only reward cannot distinguish valid reasoning from lucky guesswork with fabricated steps. Think of text generation as a sequence of decisions. At each step, the model sees the prompt plus everything written so far, that is the state, and chooses the next token, the action. For instance, if the question is 2 plus 2, after writing equals, the state includes that text, and the action is choosing the next token, say 4. This is a token-level Markov decision process. The policy is the model itself. After generating a full response, it gets a reward. In reasoning RL, the reward is typically binary. 1 if the final answer is correct, 0 otherwise. The goal is to maximize average reward. Basic policy gradient methods, like reinforce, sample many responses and update the model proportionally to the reward. But binary reward means most responses get 0 reward, so most updates are 0, and occasional non-zero updates are large and noisy. More advanced methods like proximal policy optimization use an advantage to stabilize training. Group relative policy optimization, GRPO, avoids a learned value model by using the average reward of a group of sampled responses as a baseline. The advantage for each response is its reward, minus the group average, divided by the standard deviation. FSPO builds on this GRPO framework. The paper identifies 3 mechanisms linking binary reward to increased hallucination. First, high variance gradient. When the probability of a correct answer is low, say 1%, 99% of sampled responses get 0 reward and 0 gradient. The occasional non-zero gradient is large but almost random, making training unstable and potentially pushing the model towards sequences that happen to get lucky, even if they contain factual errors. Second, entropy-driven exploration. To discover any correct answer, the model must keep its output diverse, or high entropy. High entropy forces the model to try many word combinations, including false statements. The model is forced to hallucinate as a side effect of exploration. Third, spurious local optima. If the model always outputs the same wrong answer, reward is always 0, and gradient is always 0. The model gets stuck at a stationary point with no signal to correct itself. It is confidently wrong and trapped. Together, these 3 factors explain why outcome-only RL degrades factual accuracy in intermediate steps. FSPO stands for Factuality-Aware Stepwise Policy Optimization. It starts from GRPO but adds a step-level factuality reward. First, the model's reasoning output is split into sentences. For each sentence, an automated verifier checks entailment against supplied evidence, for example, Wikipedia passages for a knowledge question. This gives a factuality reward per sentence. +1 for entailed, -1 for contradicted, 0 for neutral. The total reward combines the sentence average with the original binary answer reward. The key innovation is advantage adjustment. Instead of giving every token in a response the same group normalized advantage, FSPO adjusts each token's advantage by multiplying with a factor based on its sentence factuality. Tokens in entailed sentences get their advantage boosted, tokens in contradicted sentences get it reduced. This way, the model is rewarded more for factually consistent steps and penalized for contradictory steps, even if the final answer is correct. The authors train FSPO on a mixture of multi-hop QA with evidence and math problems. They use QWEN2.57 billion base and instruct versions, and Llama 3.18 billion instruct. On hallucination benchmarks, FSPO dramatically reduces error. For Quen base, truthful QA rises from 38 to 58%, Halu Eval from 48 to 83%, both surpassing even DeepSeek v3. On math, GSM8K rises from 65 to 89%, and MATH500 from 36 to 76%. Ablations show that the token-level advantage adjustment is crucial, outdoing both answer-only and combined reward without token adjustment. The method also transfers to Reinforce++, proving it works with different RL optimizers. FSPO builds directly on 3 previous works. From DeepSeek R1, it takes the idea of using RL to elicit reasoning, but it adds step-level factuality to prevent hallucination. From DeepSeek Math, it uses the GRPO algorithm, retaining the sampling and clipping structure, but changing the advantage computation to be token-level and factuality-aware. From R1 Searcher, it adapts the evidence-linked data pipeline, shifting the goal from teaching search behavior to ensuring faithfulness to given evidence. The paper also places itself within the hallucination survey, which organizes mitigations into pre-training, fine-tuning, and post-processing. FSPO attacks the problem at the RL dynamics level, a relatively underexplored category that modifies the training objective to reduce hallucination during learning. The paper acknowledges several limitations. The theoretical analysis assumes binary rewards, though the intuition likely extends. Experiments are limited to 7 to 8 billion parameter models, leaving larger scales for future work. The method requires external evidence and a reliable verifier, which may not be available for all tasks. Also, FSPO does not add new knowledge, it only encourages faithfulness to provided evidence. Despite these caveats, the key takeaway is that outcome-only RL creates a built-in trade-off between reasoning accuracy and factual precision, and that modifying RL training to include step-level factuality rewards can mitigate this trade-off. This design pattern, scoring intermediate steps against evidence and adjusting token-level advantages, represents a clear step toward more trustworthy reasoning models.